Welcome to the next lecture on wireless communications. Today we will look at equalization and diversity techniques. First, the brief outline for today's talk. We will briefly summarize what we have learnt in the previous lectures, followed by a very brief introduction to equalization, diversity and coding, the three techniques used to overcome the detrimental effects of fading channels. Specifically, we will look at the fundamentals of equalization followed by adaptive equalization. So, this is the agenda for today's talk. First, a brief recap. We started off with modern wireless communication systems providing us the motivation to study the various techniques for wireless communications. We looked at 2G systems, 2.5G and 3G networks. Then we moved over to the cellular concept and the concept of frequency reuse as well as co-channel interference that comes with it. We then looked at cell coverage and cell capacity. Then we studied the mobile radio propagation, where we looked at the large scale fading, which involved outdoor and indoor propagation models, as well as small scale fading, wherein we looked at relay fading and Raysian fading. We will see that fading causes a lot of degradation in the performance of any modulation technique in wireless communication, and therefore we have to devise ways and means to overcome the effects of fading. Lastly, we looked at modulation techniques for mobile communications, wherein we studied linear digital modulation techniques followed by constant envelope modulation techniques and then spread spectrum techniques. Today we will focus at how to overcome the effects of fading in some way or the other. Let us look for the motivation first. What is the need for equalization? Why do you need to equalize at all? Equalization is used for compensating inter-symbol interference. We work in a multipath environment wherein most of the time the received signal comes from several multiple paths, thereby causing inter-symbol interference. We have studied this before. The need for equalization comes in so as to overcome ISI. Earlier we had looked at certain pulse shaping techniques which can also overcome the effects of ISI, but it also comes with an extra burden. Here equalization can help overcome the effects of inter-symbol interference. That is the primary use of equalization. An equalizer within a receiver compensates for the average range of expected channel amplitude and delay characteristics. It's some way undoing the effects of the channel. It is equalizing the distortions put in by the channel. So in some case you can think of it as an inverse filter. Of course, the inverse filter may have certain problems. We will also look at those problems. The most important point for mobile communications is that equalizers must be adaptive. Why? The channel is generally unknown, and even if it is measured, it will change with time. So we must have a method to have adaptive equalization. Now another popular technique other than equalization to overcome the effects of multipath channel is diversity. Diversity is primarily used to counteract fading effects, and we have seen fading causes a big degradation in the performance of any modulation techniques. What is diversity? It is a technique used to compensate for the fading channel impairments. The different kinds of diversity techniques, what are these? Well, the popular ones are antenna diversity, frequency diversity, time, polarization, angle and code diversity. Of this, antenna diversity is one of the more popular ones wherein we use multiple antennas. Now, these multiple antennas can be either at the transmitter or at the receiver, or both. Frequency diversity requires you to use frequency signals which are separated by the coherence bandwidth of the channel. We have looked at frequency diversity in our previous lectures. Time diversity, we must separate the transmission more than the coherence time of the channel. We will revisit the coherence bandwidth and the coherence time briefly to refresh our memories. Polarization diversity, okay, the horizontal and the vertical polarized signals fade differently and independently. Angle diversity, and use different codes, so you can have code diversity. So, the popular antenna diversity is implemented by using 2 or more receiving antennas, and as I mentioned before, you can also have them at the transmitter. Now, while equalization is used to counter the effects of ISI or inter-symbol interference, diversity is usually employed to reduce the depth and duration of fades. That is the fundamental difference. So, the depth of fade and the duration of fades experienced by a receiver in a flat fading scenario can be overcome by using diversity. Okay. These techniques can be employed both at base station and mobile receivers. Any of the diversity techniques can be deployed either at the base station or at the mobile receivers. Spatial diversity is the most widely used diversity technique. Right? You can have multiple antennas at the base station, because having multiple antennas in your handset is a little inconvenient, or you can even have antennas on different base stations. So, you really get a good spatial diversity. The key point in spatial diversity is the separation of the antenna elements. Depending upon how cluttered is the multipath environment, your antenna separations may have to be increased or decreased. Let us talk about spatial diversity. In this technique, multiple antennas are strategically spaced and connected to common receiving system. While one antenna sees a signal null, one of the other antennas may see a signal peak, provided the signals are not correlated. In this case, the receiver is able to select the antenna with the best signal at any time, or it can do some kind of an intelligent combining. The CDMA or code division multiple access systems use rake receivers which provide improvement through time diversity. Now, let us look at the diversity techniques. Unlike equalization, diversity requires no training overhead, as the transmitter does not require one. Today, we will see that equalization has 2 modes, the training mode and the tracking mode. The training mode will require us to send a known signal, and it is used to set the weights of the equalizer, whereas diversity does not have that issue. What else does diversity techniques do? It provides significant link improvement with little added cost. It also exploits random nature of wave propagation by finding independent and hence uncorrelated signal paths for communications. That is how diversity works. It is a very simple concept wherein one path undergoes a dephase and another independent path may have a strong signal component. That is it. Okay? If you cast several nets, you are bound to catch fish in one of them. That is the basic philosophy. As there is more than one path to select from, both the instantaneous and average SNRs at the receiver may be improved, often as much as 20 to 30 dB. Please recall from one of your earlier lectures that when you have to have an improvement in bit error rate as compared to additive wide Gaussian noise channel, fading channels require 20 to 30 dB additional SNR for the same performance. Here in diversity techniques you overcome that. Now the third and also a very popular method to overcome the impairments put in by the channel is called the channel coding. It's sometimes also referred to as error control coding, because the objective is to detect and recover from errors introduced by noise and fading. So what is channel coding? It is a technique which improves mobile communication link performance by adding redundant bits in the transmitted message in a known manner. That is key. We add redundancy in a known manner so that there is some kind of a structure built into the message. At the receiver, because of the noise or fading, the structure gets disturbed. But we can kind of guess and hence recover from errors based on the algebraic structure of the code. In this technique, the baseband portion of the transmitter, a channel coder maps a digital message sequence into another specific containing greater number of bits than originally contained in the message. All it means is that I have a mapping from k bits to n bits where n is larger than k. That is, I add n minus k redundant bits, but in a known manner. The coded message is then modulated for transmission over the wireless channel. Channel coding is used by the receiver to detect or correct some of or all of the errors introduced by the channel. It depends upon how strong is your error correcting code. In fact, it is a design problem. If you have a channel which is a bad case scenario, then you must use a stronger code wherein you have to use more number of redundant bits. The added coding bits lower this raw data transmission rate through the channel. In fact, if you are mapping k bits to n bits, then k over n is given as the code rate of the code. There are two types of codes, broadly speaking. One is block codes and then there is convolutional codes. Convolutional codes are codes with memory. Now let us revisit very briefly the concepts of coherence bandwidth, coherence time and delay spread, because we will realize that diversity techniques, equalization techniques and coding techniques individually or in combination must be used in different channel conditions, whether it is frequency flat fading, frequency selective fading, fast fading or slow fading, right. So we must come up with a matrix which can help us put things in perspective, which technique to use in which fading environment. So let us revisit RMS or root mean square delay spread. What was that? It characterizes the time dispersiveness of the channel obtained from the power delay profile of the channel, indicates delay during which the power of the received signal is above a certain value. It is the square root of the second central moment of the power delay profile, and sigma subscript tau is given by under root tau squared bar minus tau bar squared, which is the second central moment of the power delay profile. Tau squared bar is calculated as follows. What is coherence bandwidth? We define coherence bandwidth as the range of frequencies over which the frequency correlation is above 0.9. This is one of the possible definitions of coherence bandwidth. In this case, BC, coherence bandwidth, is given by 1 over 50 sigma tau. On the other hand, if you want to have a linear definition wherein we define coherence bandwidth as the range of frequencies over which frequency correlation is above 0.5, in that case coherence bandwidth is 1 over phi sigma tau. Okay. So sigma tau comes directly from measurement data, and then by this basic formulae I can find out the coherence bandwidth compared to the signal bandwidth, if your coherence bandwidth is larger or smaller, you decide whether the channel is frequency selective or frequency flat. Now, the other dimension is coherence time. Coherence time is a statistical measure of time duration over which the channel impulse response is essentially time invariant. It tells us how fast the channel is changing in time. If the symbol period of the baseband signal is greater than the coherence time of the channel, then the channel will change during the transmission of the signal. Hence, there will be distortion at the receiver. How do we define coherence time, Tc? Tc is approximately given by 1 over Fm, where Fm is the maximum Doppler spread. Okay. So, coherence time will tell us whether your channel is fast fading or slow fading, and thereby help us figure out whether to use equalization, diversity, or coding, or a combination. So, let us see the types of small scale fading. Based on multipath time delay spreading, we have either a flat fading or a frequency selective fading. The conditions are pretty simple. Bs much less than Bc. Bc is the coherent bandwidth, Bs is the bandwidth of the signal. If the bandwidth of the signal is much smaller than the coherence bandwidth, we encounter flat fading. On the other hand, if Bs is greater than coherence bandwidth, then we expect to see some kind of a frequency distortion. We also will see intersymbol interference, and thereby there will be a need for equalization. So, here in the orange is the channel bandwidth, coherence bandwidth of the channel, in the green is the signal bandwidth. In the first case, clearly in the frequency domain you can see that your signal frequency spectrum will not get distorted, whereas here your signal is much broader in the case of frequency selective fading than the channel coherence bandwidth, and you will encounter a lot of intersymbol interference. Flat fading occurs due to fluctuations in the gain of the multipath channel, which leads to change in the amplitude of the received signal with time. For example, Rayleigh fading occurs when symbol period of the transmitted signal is much larger than the delay spread of the channel, may cause deep fades, and increase in the transmit power to combat this situation may help. But what we saw last time is that the requirement, the fade margin that you have to put in is tens of dBs. So, it is not a very good way to overcome. The easier, cheaper, more effective solution is to use some kind of a diversity. So, flat fading channel characteristic, you have the signal, this is your fading channel, and this is the received signal. Here St in time domain looks like this, and as we have seen, we have a flat fading scenario. So, Ht is a narrower impulse response here, and if you convolve these two, you get Rt. In the frequency domain, you have S of f, H of f, and multiplication gives you R of f. This is the frequency flat channel characteristic from the time and the frequency domain. Now, let us see how we fill in our matrix. So, here we have on this axis flat frequency flat fading and frequency selective fading. These two depend on the coherence bandwidth of the channel. On this axis we have slow fading and fast fading. This depends on the coherence time of the channel. Now, if you look at the first location in this grid, which is frequency flat slow fading channel, there we can use diversity. We have seen that diversity works well for flat fading. Similarly, even if it is flat but fast fading, you still have the choice of diversity technique. On top of that, you can also use coding and interleaving. So, interleaving is a technique which we studied in previous classes, where it causes a little bit of delay in the signal. We have a memory wherein read in row wise, read out column wise, at the receiver read in column wise and read out row wise. Okay. It is used to spread out the burst errors. So, both diversity techniques and coding plus interleaving techniques will work for flat fading scenario. Clearly, equalization will not be effective here. Equalization becomes effective in a frequency selective environment. Equalization has been designed to overcome the distortions put in by the channel. It is an inverse filter, right? And if you have frequency selective but fast fading, right, then I may not have the time to effectively track the channel, and therefore I might have to resort to diversity and coding and interleaving again. So, this is a handy reckoner which helps us figure out which of the three techniques or a tandem of them could be used for flat slow, flat fast, frequency selective slow and frequency selective fast fading channels. Now, let us look carefully at equalization. We start off with fundamentals of equalization. We have learnt so far that equalization is used to eliminate or reduce the effects of inter-symbol interference. ISI has been recognized as a major obstacle to high speed data transmission. Earlier in the lectures, we had done a basic calculation for different kind of fading channels and how fast you can send data without equalization, and we saw that the rates were pretty dismal. So, if you have to go in for high speed data transmission, we have no choice but to use some kind of equalization technique. Even GSM provides for equalization, though the standard does not specify a particular type, and the manufacturers are free to use some of their proprietary equalization techniques. Equalization, as we know, is used to combat inter-symbol interference. As the mobile fading channels are random as well as time varying, equalizers must track the time varying characteristics of the mobile channel and thus are called adaptive equalizers. There is also an interesting concept which is called blind equalization, wherein it does not need a training sequence. It uses some property of the signal, maybe constant envelope or constant amplitude, so as to guess the distortions being put in by the channel and undo those effects. But the more common ones are adaptive equalizers, which work on the concept of a training sequence. So, let us look at adaptive equalizers. The two operating modes of an adaptive equalizers are training mode and tracking mode. The training mode precedes the tracking mode. In the training mode, we have to send a known or a sequence or a PN sequence in order to understand how the channel is. It is basically a method to measure the channel frequency response, and then fix your weights accordingly in order to overcome the effects of channel. And then is a tracking mode. If the channel changes fast, then you have to resort to training mode again, and then when you are happy with the estimate of the channel, then you go back into the tracking mode, and you keep switching between the training and the tracking mode. Let us talk about the training mode of adaptive equalization. What do we do in a training mode? Initially, a known fixed length training sequence is sent by the transmitter so that the receiver's equalizer may average to a proper setting. The training sequence is usually a pseudo-random sequence or a fixed known prescribed bit pattern usually put in the standard. So you know what you are sending. Immediately following the training sequence, the user data is sent. Now let us talk about the training sequence. The training sequence in an adaptive equalizer is designed to permit an equalizer at the receiver to acquire the proper filter coefficients in the worst possible channel conditions. So it says a lot of things here. It talks about filter coefficients. So we will see in later slides that your equalizer could be like a finite impulse response FIR filter which has filter coefficients, or it can look like a tap delay line with weights. So we have to figure out what the weights should be. But please note that the training sequence is kept in mind so that we can account for the worst possible channel conditions. What could be the bad channel scenarios? Maximum delay, deepest fades, maximum intersymbol interference. Right? So these are some bad conditions, and when we design the training sequence, we must keep in mind the worst case scenario. You should be able to account for these worst case scenarios as well. Therefore, when training sequence is finished, the filter coefficients are near optimal. An adaptive equalizer at the receiver uses a recursive algorithm to evaluate the channel and estimate filter coefficients to compensate for the channel. So it has to be some kind of a recursive method which finally converges to the exact optimal value or close to the optimal value. Now we move over to the tracking mode. What happens once you have been able to fix your filter coefficients? When the data of the users are received, the adaptive algorithm of the equalizer tracks the changing channel. So therefore, we must have a notion of an error, and it has to be possibly a feedback equalizer, but that is not the only kind of equalizer possible. So as a result of this, the adaptive equalizer continuously changes the filter characteristics over time. So whenever you do an analysis of the filter coefficients, you should have a time index associated with the weights of the filter. The weights of the filter changes continuously with time in the tracking mode. We never fix it and forget it because of the time varying nature of the wireless communication systems. Equalizers are widely used in TDMA systems. Let us now look at the block diagram of an adaptive equalizer. Let us say we have the original baseband message x of t. It passes through a modulator, then through the transmitter over to the radio channel. Here noise and fading effects get added, leading to a very distorted received signal. Here it goes through the RF receiver front end, passes through the IF stage, and then detector and matched filter. So your equalizer usually works either at the IF stage or at the baseband. So here is your equalizer, decision maker, an error which kind of tracks, and then finally you have the reconstructed message data dt. Fine. In the training section, this dt and xt should be equal because you know what your dt expected dt should be. Let us now look at the working of an adaptive equalizer. The signal received by the equalizer is simply given by yt. What is it? xt convolved with f star t plus np. If you go back here, ft is the combined impulse response of the transmitter, multipath radio channel, and the receiver RF IF. Here is the ft. Right? xt is what you send. So, if you convolve this and then add your noise nbt, you get yt. This is the input to the equalizer as shown here, yt, equalizer input. nbt, the subscript b, stands for the baseband noise. If the impulse response of the equalizer is h equalizer t, the output of the equalizer is xt convolved with f star t convolved with h equalizer t plus nbt convolved with h equalizer t. You convolve y of t with your h equalizer, which can be written as xt convolved with another term gt plus nbt convolved with h equalizer t. gt is f star t convolved with h equivalent h equalizer t. So, f star t convolved with h equivalent equalizer t gives you gt here. The desired output is xt, which is the original source data. Assume that nbt is 0 for the time being. In order that dt is equal to xt, what is dt? If you go back here, dt is the reconstructed message data and xt is the original baseband message. If you want these to be the same, in that case gt, which I have already defined as f star t convolved with h equalizer t, should be a delta function, delta t. Only then you will have dt same as xt in the absence of a baseband noise. So, the main goal of the equalizer is to satisfy this above equation. In frequency domain, the same thing is given by h equalizer f star minus f equal to 1. So, the time domain and frequency domain implementation are the two basic equations that have to be satisfied for any equalizer to work effectively. So, we start from the frequency domain, h equalizer f times f star minus f is equal to 1. What does it take? It implies simply that the equalizer is kind of inverse filter of the channel, right? If the channel is frequency selective, the equalizer enhances the frequency components with small amplitudes, working as an inverse filter, and attenuates the strong frequencies in the received frequency spectrum, so as to obtain a flat composite received frequency response, and on top of that a linear phase response. So, that is the basic philosophy of working of an adaptive equalizer. It works as an inverse filter by enhancing the frequency components of small amplitude and attenuating the frequency components with larger amplitudes, in the same time keeping in mind that a linear phase response is obtained. For a time varying channel, the equalizer is designed to track the channel variations so that the above equation is approximately satisfied. Now, let us look at a generic adaptive equalizer. How does it look like? Why does it work the way it is designed to work? Suppose your input is yk, it passes through something that looks like a tapped delay line. So, delay 1, delay 2, so and so forth. So, there are n points and then there are n plus 1 taps. Here each of these tapped values is multiplied with a weight given by this weight vector w0k, w1k, so and so forth up to wnk. So, there are n plus 1 weights. Please note, besides this w0, w1 and so and so forth, a k denoting the time index has been put. We have observed earlier that these weights must change with time. Then we have the estimate decay hat, we have the decay, there is an error, and this error is used to update the weights. How we do it? There are various techniques to do it. We will talk about those techniques. So this is the generic block diagram of an adaptive equalizer. So, what is an adaptive equalizer in principle? An adaptive equalizer is a time varying filter which must constantly be retuned. In the block diagram, the subscript k represents the discrete time index. Here k is the discrete time index. It can be seen from the block diagram that there is a single input yk at any time instant here. The value of yk depends on the instantaneous state of the radio channel and the specific value of the noise. The block diagram shown is called the transversal filter, and in this case it has n delay elements, n plus 1 taps, and hence n plus 1 tunable multipliers, which we will call weights. So, here is my weight vector. These weights have a second subscript k, as pointed out earlier, to explicitly show that they vary with time and are updated on a sample by sample basis, or in some cases for the whole block. So, either you work sample by sample or you work with the whole block. The adaptive algorithm is controlled by the error signal Ek. The error signal is derived by comparing the output of the equalizer with some signal Dk, which is either a replica of the transmitted signal Xk or which represents a known property of the transmitted signal. So, either we have the luxury of knowing what Xk is or with some property of the transmitted signal. The adaptive algorithm uses Ek to minimize the cost function and uses the equalizer weights in such a manner that it minimizes the cost function iteratively. This is important. How many iterations will it take to converge? Those depend on the particular choice of the algorithm. The least mean square or LMS algorithm searches for the optimum or near optimum weights. This is one of the popular methods. Now, let us see how the weights are updated. New weight is previous weight plus a constant times previous error times current input vector, where previous error is previous desired output minus previous actual output. So, very simple scheme for updating the weights. Here the constant shown here may be adjusted by the algorithm to control the variation between filter weights on successive iterations. This process is repeated rapidly in a programming loop while the equalizer tries to converge. When the convergence is reached, the algorithm freezes the filter weights. Okay. So, this is the basic way how the adaptive equalizer works, how the weights are updated. So, there is a recursive algorithm trying to freeze the filter weights. Let us talk about the mean square error. From classical equalization theory, the most common cost function is the mean square error, or MSE, between the desired signal and the output of the equalizer. The mean square error is represented by the expected value Ek times E star k. When the replica of the transmitted signal is required as output of the equalizer, a known training sequence must be periodically transmitted. We know this already. By the detection of the training sequence, the adaptive algorithm in the receiver is able to minimize and the cost function by driving the tap weights until the next training sequence is sent. When is the time to change the training sequence or go to the training mode? It depends on how fast the channel is changing. Let us now quickly look at the basic mathematics involved with an adaptive equalizer. Let us define the input signal to the equalizer as a vector yk, where yk in boldface is yk minus 1 up to yk minus n transpose. So, it is a column vector. The output of the equalizer is a scalar and is written simply by dk hat is equal to summation from n is equal to 0 to n. So, there are n plus 1 terms wnk, the weights, multiplied with the appropriate delayed version of the input signal, comes from the basic block diagram. The weight vector can be written as follows: W0k, W1k, and so on and so forth up to Wnk transpose. Using the previous two equations, we have dk hat is nothing but yk transpose times wk is equal to the wk transpose yk. When the desired equalizer output is known, right, in the training phase, dk is nothing but xk. Then the error signal ek is given by dk minus dk hat, the estimate of dk, but dk is xk, so xk minus dk hat. So, from the equation number 4, here we have the error ek is equal to xk minus yk transpose wk is equal to xk minus wk transpose yk. Now, to compute the mean square error, the mod of ek squared at the time instant k must be taken, right. So, equation 6 is squared to obtain ek squared, and you square the right hand side too to obtain equation number 7. And now, when you take the expected value of ek squared over k, which in practice amounts to computing time average, yields the following equation: expected value xk squared plus wkt. We assume this is out of the expectation operator, expectation over time, because we expect the weights have converged, e yk transpose. So, this is what we measure. So, it is easily available to us, wk minus expected value xk yk transpose complex conjugate wk. It should be noted from equation 8 that wk is not included in the time average, since it is assumed that it has converged to the optimal value. It is also noted that xk and yk are not independent, otherwise it was fairly easy to simplify the equation, and there should be an input vector correlated to the desired output vector of the equalizer. So, we define the cross correlation vector p as follows, which is nothing but the expected value of xk yk given by this. And let us define the input correlation matrix of the order n plus 1 by n plus 1, and let us represent it by R. R is nothing but the expected value of yk, yk transpose, and given as follows. Notice the principal diagonal. It is yk squared, yk minus 1 squared, and so on and so forth. So, it is the power at the kth instance, the k minus 1th, and so on and so forth up to k minus nth instant. Note there is an expectation operator outside, and these are the correlations, cross correlation between the tapped delay points. So, the matrix R is also called as the input covariance matrix. The diagonal of R contains mean square values of each input sample, and the cross terms specify the autocorrelation terms resulting from the delayed samples of the input signals, as observed before. Now, if xk and yk are stationary, then the elements r and p are second order statistics that do not vary with time, and hence using these equations we have the mean square error given as follows. Mean square error is equal to expected value of xk squared plus weight vector transpose r weight vector minus 2 p transpose weight vector. So, this is the expression we have for mean squared error. We have to minimize the mean squared error so as to obtain the optimal weight values. Okay. So, please note r can easily be computed if you know the y, yk, yk minus 1 up to yk minus n. Right. So, let us now summarize today's lecture. Today we talked about the use of equalization, diversity and coding. We saw that fading channels cause major impairments in the modulation technique performance simply because of getting into deep fades and the fade duration that we stay within the faded region. Equalization is a very simple, inexpensive method to overcome the effects of fading, but it works only when there is a frequency selective environment. Equalization is used for intersymbol interference. Diversity on the other hand can be used in most of the cases, and we use any one kind of diversity or a combination of diversity. We saw there is a series of possibilities. For example, you have the space diversity, the time diversity, the frequency diversity, the polarization diversity, the angle diversity, or even the code diversity. The third method is also popular to overcome the channel impairments put in by fading channels. It is called coding. Coding basically requires you to add redundant bits in a known manner in the transmitted signal, so that at the receiver you can detect and probably correct the errors. Coding is often used with interleaving in fading environments. There is an advanced technique which combines coding with modulation called trellis coded modulation as an example, or a block coded modulation, wherein we use the effects of coding together with modulation, because the objective of modulation is also to have a good bit error rate performance, and same is the objective of channel coding. So, you can combine them together to use coded modulation. We then moved over to the study of the fundamentals of equalization, why it works, what is the basic structure of an equalizer. Specifically, we talked about adaptive equalization and how weights of the equalizer may be adjusted depending upon the input signal. We saw that equalizations work in two modes, the training mode and the tracking mode. The weights, however, always have a time index, that is, they change continuously with time. Fading channels and mobile channels in particular provide you with time varying channels, and hence your equalizer must be fast enough and should converge to the optimum value at the earliest. In the next few lectures, we will look at more details about equalization, diversity and coding. We will conclude today's lecture here.